We're going to continue talking about the linear model and the regression line for this video, and we're going to start with the slope. So if you remember from algebra, slope is rise over run, so your y values over your x values. So that still holds true here. So the equation for our slope, or b sub 1, is r times s sub y over s sub x. R is our correlation coefficient, and s sub y and s sub x are the standard deviation of your y and x variables. And note that the standard deviation of the y variables is over the standard deviation of the x variables. So that will be the equation that we use to calculate the slope. The y-intercept also has a formula that we can use to be able to calculate it. First, though, we have to remember that the line of best fit will always cross the mean point, x bar comma y bar. Therefore, the y-intercept can be found using this equation, which is b sub 0, which is your y-intercept, equals y bar minus b sub 1, which is your slope, times x bar. So you use your slope and your mean point to be able to find your y-intercept. Both equations I will give you because both equations will be given to you for the AP test. But you will have to know what b sub 1 and b sub 0 and x bar and y bar represent. But again, when you are calculating the y-intercept, you want to make sure that you find the slope first and then find the y-intercept. So when we're using the linear model, again, there are assumptions and conditions. They are the same three conditions. Quantitative variable condition, so both variables are quantitative, meaning they have units. The straight enough condition, so our scatter plot is straight, and then our outlier condition. We want to make sure that there are no outliers. So for example, we're going to be using the same example that we kind of started out with in the previous video. So in a scatter plot that plots the amount of protein in a Burger King burger versus the amount of fat in a Burger King burger, we end up finding out that the mean fat content was 23.5 with a standard deviation of 16.4. The mean protein content is 17.2 grams with a standard deviation of 14, and it has a correlation coefficient of 0.83. So continuing with the example, the mean point then is 17.2, 23.5. Our standard deviation of our y variable is 16.4. Standard deviation of our x variable is 14. And our correlation coefficient is 0.83. This is all we need to be able to find our slope and our y-intercept. So here we have b sub 1, which is our slope, and we have to calculate that first. So we do that by taking our correlation coefficient and multiplying it by the standard deviation of our y variable, divide it by the standard deviation of our x variable. So we end up with 0.97 as our slope, and again, it's y over x. To calculate the y-intercept, once we have our slope, we just plug it into the previous equation. So we take the mean y variable minus our slope times our mean x variable, and we end up with 6.8. And again, the reason why we can use the mean point is because we know that the line of best fit will always cross through the mean point, so we know that that point is on our line. Then, when we're writing our model in context, because remember, context is important, we don't use x and y for our variables. We plug in what our x and y variables actually represent. So our y variable was the fat, so it still has to have a hat, because that hat is indicating that that's going to be a predicted value. So our predicted fat is equal to 6.8 plus 0.97 times the protein. So instead of x, we use protein because protein was our x variable. And writing it like this means that it is in context, and that's what we're looking for. Once we have the model, we want to know, what does this equation actually tell us? Our slope will tell us how the variable changes in units of y per x. So in our Burger King situation, every gram of protein added 0.97 grams of fat. So I'm going to go back to the equation. So our equation is our predicted fat equals the 6.8 plus the 0.97. So again, this is our slope. So if we have 1 gram of protein, we multiply that by our slope. So we're going to be adding 0.97 grams of fat for every gram of protein because it's going to be equal to the fat. So one more time, each gram of protein will add 0.97 grams of fat. What does the intercept tell us then? I've already said that the y-intercept kind of is useless in most cases, and that holds true. And most often it serves as a starting point, not an actual prediction value. Sometimes it is useful, but most of the time it's really there just to make sure that the equation fits our data. Looking at another example, if we look at the relationship between house prices and house size, where the price is measured in thousands of dollars and the size is measured in thousands of square feet, we get the regression model of price equals 9.56 plus 122.74 times the size. So our y variable is our price and our x variable is our size, which means our slope is going to be 122.74 and our y-intercept is 9.56. So the first thing we want to know is, what does the slope of 122.74 mean? Well, in this case, it means that for every square foot, the price goes up $122.74, or $122.74. We always interpret the slope as the unit of x will either increase or decrease by the slope using the units of y. So for every square foot, which is the unit of x, the price in this case goes up because we're adding, goes up by the slope, 122.74, and then we use the y unit, so price was measured in dollars. Now, I want to note that the units were actually thousands of dollars and thousands of square feet. Because both are measured in thousands, we can look at it as 1-to-1. However, a more appropriate way of saying this might be to say for every 1,000 square feet, the price goes up $122.74 thousand. So you want to be careful with your units. Again, then we want to know, what are the units? So your units are always going to be your y units over your x units. Remember, it's your slope. Slope is rise, which is your y variable, over run, which is your x variable. So y over x. So in this case, it would be dollars per square feet, or again, because they were actually measured in thousands, it would be thousands of dollars per thousands of square feet. And then the last question, we want to know how much would we expect to pay for a house that is 3,000 square feet. Now, our equation is scaled down because the unit is measured in thousands. So this is 3,000. So instead of actually plugging 3,000 into our x variable, we only plug in 3 because our units are talking about in thousands. Then we would just follow order of operations. We'll multiply first and then add, which would give us $377.8 thousand, which correlates to $377,780. So that's all we have for today. Again, we will spend more time in class practicing how to calculate and interpret the linear model, and that interpretation is going to be key. We have to know how to do that, including keeping it in context and understanding the slope and how to make predictions. All right, but that's it. So I will see you guys tomorrow. Have a great night.